Mathematical induction is a way to prove special types of statements. In particular, what we're trying to prove is we're trying to prove a statement is true when n is an integer greater than or equal to some fixed integer, usually greater than or equal to 1. Okay? Before we do this, I want to just do a quick review of what an open sentence is. And as such, we'll just do an example. Suppose that P of n is the statement n squared minus 4n is greater than or equal to 6. And so we look at the statement P of 2, and what we do is where we see an n, we substitute 2 in for n. So we'd have 2 squared minus 4 times 2. Well, that's 4 minus 8, which is negative 4. Negative 4 is certainly not greater than 6, and so this statement is false. Let's look at another one. P of 10, here we'd take 10 squared minus 40, that's 60, which is certainly greater than 6, greater than or equal to 6. Okay, so our goal in mathematical induction is to prove statements that are of this form. P of n is true for all n greater than or equal to 1. Now sometimes we might actually, instead of saying 1, we might say some number a instead. To motivate this, we look at an example. This is a pretty nice example. What's the sum of the first n positive integers, odd integers that is? We collect some data. We see that 1 plus 1, or 1 is 1. That's pretty boring. That's the sum of the first one odd integer. The sum of the first two odd integers is 4. First 3 is 9. First 4 is 16, and so on. We notice that these numbers are perfect squares. When I added the first 5 odd integers, I got 5 squared. The sum of the first 4 odd integers is 4 squared. So we're going to let P of n basically be that observation, that the sum of the first n odd integers is n squared. Now it might take a little bit of convincing that the last term in here is truly the nth odd integer. And if you just take a quick look at 9, for example, 2, we're claiming that 9 is the 5th odd integer, so 2 times 5 minus 1, yep, that's equal to 9. So our goal is to prove that this statement is true whenever n is greater than or equal to 1. So here's how we prove these types of statements. We're going to prove a statement, a universally quantified statement, for all n greater than or equal to 1, P of n is true. PMI is a principle of mathematical induction. The first thing we're going to do is we show that P of 1 is true. Now, 1 might be some other number a. Maybe it's not, the statement is not true when n is equal to 1. Maybe it's only true when n is equal to 4, 5, and so forth. Okay? But we'll show that some initial value is true, and this is known as the base case. Next, we're going to assume that our statement P of k is true for some k greater than or equal to 1, which is our starting value. So if I was using a as my starting value, I would assume that P of k is true for some k greater than or equal to a. This is what's known as the inductive hypothesis. We say it's the hypothesis because a hypothesis is something that we assume to be true, and so we're assuming that P of k is true. Then we're going to use the fact that P of k is true to show that it's true for the next statement. So just verbally, what are we doing with our example? We said that sum of the first n, or first k odd integers would be k squared, so we would assume that to be true, and then we'd have to prove that the sum of the first k plus 1 odd integers is k plus 1 squared. Well, why does it work? Remember that we said we have to show that P of 1 is true. And then we're also going to show that P of k implies P of k plus 1. So this is all one statement. Well, if P of 1 is true, I can substitute 1 in for k here. That would say that P of 1 is true means that P of 1 plus 1 is true. So this altogether, these two statements together, P of 1 being true, and whenever P of k is true, P of k plus 1 is true, that would tell me that P of 2 is true. Okay, so P of 1 is true. If P of k is true, then P of k plus 1 is true. Well, since P of 1 is true, the next value of n will be true as well. Well, now I know p of 2 is true, so now I know p of 2, and I know that if p of k is true, then p of k plus 1 is true. I can conclude that p of 3 is true, and so on. And we can show that p of 4 is true, and then p of 5 is true, and so all of them will be true. So let's go ahead and do this for our particular example. So we're going to prove that the sum of the first n odd integers is n squared. All right. The first thing we do is we're going to say p of n is this statement, and then we're going to show that it's true when n is equal to 1, because that was where we start, n greater than or equal to 1. Had the problem said prove that for any integer greater than or equal to 12, I would not do p of 1, I would do p of 12 instead. So we do this individually. Figure out what the left-hand side of the equation is going to look like. Well, I know that I'm adding up the first n odd integers, and if n is 1, that means I'm taking the first one odd integer, but I can actually plug the number 1 into my formula, and it says I'm going to add up from 1 up to 2 times n minus 1. Well, n is 1, so I'm going to add up from 1 to 2 times 1 minus 1. 2 times 1 minus 1 equals 1, and so I'm going to add from 1 to 1. I stop at 1. So the left side is 1, the right side is n squared. When n is 1, we get 1 squared, which is also 1. So the statement is true when n is equal to 1. Now we're going to suppose that the statement is true for some number k greater than or equal to 1. Now we know it's true when n is equal to 1, but we're putting that aside for a moment. We're just going to suppose it's true for some number k greater than or equal to 1. In other words, what we assume is that we basically take our statement p of n and replace n by k. Remember, it went 1, 3, 5, 2 times k minus 1, and then k squared. Now, I skipped. Remember, there are a whole bunch of other odd integers in that little dot, dot, dot. So don't forget that that's there. We have to prove that it's true when n is equal to k plus 1. So what we do is we go back to our statement p of n, which looked just like this guy up here, except k was n, and this was n squared. Okay, I'm going to replace n here and here by k plus 1. Okay, now there's something kind of odd here that people tend to object to. I replaced n, that was where my n was, so it's 2 times not n, but 2 times k plus 1. So there's 2 times k plus 1, and then I have my minus 1. This we said was n squared before, and we're replacing n by k plus 1, so instead of n squared, we get k plus 1 squared. Now everybody objects, hey, why did you have this extra 2 times k minus 1 in there? Well, because this is a sum of n terms, in general, for the statement p of n. When I go to the next statement, I should have n plus 1 terms. So I keep all the terms that I had before, and I tack on a new one. Okay, remember, I keep all the terms I had before, I tack on a new one. So in general, for the summation type problems with mathematical induction, often what we'll do is we'll just keep the old sum and just tack on an extra term. We simplify, and if I distribute, I'd have 2 times k, and then 2 times 1, which would be 2. 2 minus 1 would give us plus 1. And this makes perfect sense. How far apart are our odd numbers spaced? They're spaced 2 apart. So if the nth, or in this case the kth, odd integer is 2 times k minus 1, if we add 2 to it, we would get 2 times k plus 1. So this is our goal. Big goal. We want to prove that this is true. And we get to use this. Okay, I'm going to say this is a fact, even though I'm only assuming it's true. And I know that people have objections to that. But we're going to say, hey, this is true. I can use this in order to prove this. All right? Now, here's the key. We're going to start off by taking only one side of the equation that we had in the previous slide. So we're only going to take one side and show that this transforms into the other side. So my goal is to get this to be equal to k plus 1 squared. Okay, and you can see my excitement here. Wowie zowie, this guy is equal to k squared. We assumed that 1 plus 3 plus 5 up to 2 times k minus 1 was equal to k squared. So I can replace all this by this nice little simple k squared over here. And we say this is justified by the induction hypothesis. And the induction hypothesis was that this quantity here was equal to k squared. Well, now I'm at the point where I want to take k squared plus 2k plus 1 and see what I can do with that. And remember my goal. My goal is I want to get k plus 1 squared. Okay, but if we just factor, k squared plus 2k plus 1 does factor as k plus 1 squared, and so we just showed that the sum of the first k plus 1 odd integers is equal to k plus 1 squared. So p of k plus 1 is true, again, assuming that p of k is true. Since now we get to show off, since p of 1 is true, and p of k implies p of k plus 1, that's what we just showed, we know that p of n is true whenever n is greater than or equal to 1. So another example, just to help out with the understanding, we're going to prove that the sum of the first n integers, positive integers, 1 through n, is equal to n times n plus 1 over 2. If I add up the first n integers, positive integers, it's n times n plus 1 over 2, whenever n is greater than or equal to 4. Okay, I'm being a little bit obnoxious here. Why did I say n is greater than or equal to 4? Because I wanted to. That's how you're going to have to take it. For the base case, we're going to show that it's true when n is equal to 4. So the sum of the first 4 integers, positive integers, should be 4 times 4 plus 1 over 2. So the left side is 1 plus 2 plus 3 plus 4, which we can calculate and get 10. On the right side, we plug 4 in for n. 4 times 4 plus 1 is 4 times 5, which is 20, divided by 2 is 10. So it's true when n is equal to 4. Now, I will admit I'm being obnoxious here. It's true when n is equal to 1, 2, and 3 as well, but I just wanted to demonstrate we don't have to always start at n equals 1. Okay? So I started a little bit later there. All right, so now let's suppose the statement is true for some integer k greater than or equal to 4. Why did we say greater than or equal to 4? Because that was my base case. And so we're going to suppose that this is true. Again, all we did was we took our original equation and replaced n by k. We're trying to prove it's true when n is equal to k. So our goal then is to prove that the first k plus 1 integers, when added up, will be equal to, well, it's a little bit more complicated here. I'll get to that in a moment. But again, notice that I kept the sum of the first k integers, and then I threw on an extra term. Now remember, our original statement had n times n plus 1 over 2. What I've done is I've replaced n by k plus 1. And here I've replaced n by that k plus 1. Okay, so we have k plus 1 times k plus 1 plus 1, which is k plus 2. So I want to show that this is equal to this. This is my goal. Okay. In induction proofs, you always want to keep your eye on the goal. Also, you only want to work with one side of the equation. It is not proper to say this equals this and then manipulate both sides. That's not proper way to prove these things. Okay, so we're going to start off with the left-hand side of the equation. I make my little wowie-zowie revelation. There's the sum of the first k integers. And I assumed that that sum was equal to k times k plus 1 over 2. So I'm going to replace this by k times k plus 1 over 2. That's the inductive hypothesis. There's my k times k plus 1 over 2. And then I still have this term k plus 1. A lot of these problems, not all of them, will have some nice things that can be factored. Okay, so notice that I have k plus 1 in each term. Okay, so we're going to factor out. All right, so simplifying, we're going to factor out k plus 1. When I factor it out of the first term, I'm only left with k over 2. Okay. When I factor it out of here, you got to be careful. We aren't left with nothing. Remember, factoring is kind of like dividing. If I divide k plus 1 by k plus 1, I get positive 1. The alternative is to multiply by an imaginary 1 there. That doesn't change the value at all. When I factor it out, I'll still be left with that 1. Now remember, my goal is to get k plus 1 times k plus 2 over 2. Well, let's work on that guy. 1 is 2 over 2. We're getting a common denominator. Combine it into one fraction. It's starting to look good. K plus 1 times k plus 2 all over 2. We achieved our goal. So the statement is true whenever n is greater than or equal to 4 because it was true when n was equal to 4, and we proved it was true when n was k plus 1 whenever it was true when n was equal to k.